Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And also, we have a free MSE Company Database categorized by industry sector, location, as well as internship and full-time titles. So if you're interested in that, you can find the link in the description below.
Our sponsor today is Johnson Matthey. Are you a material scientist or engineer who wants to be part of the drive for a world that is healthy and cleaner, both for today and for future generations? By understanding the relationship between a material structure and its physical properties and chemical behavior, material scientists and engineers at Johnson Matthey develop sustainable technologies that are catalyzing the zero transition in transport, chemicals, and energy. They design porous materials for catalyst supports for emission control systems that remove harmful emissions produced by diesel and gasoline engines. They innovate new compositions for catalysts at the heart of the hydrogen fuel cells in trucks and buses. And they also develop new corrosion-resistant reactors for processes that enable the production of sustainable chemicals and fuels. To find out more, visit matthey.com, that's MATTHEY.com. Johnson Matthey, inspiring science, enhancing life.
Hello, welcome back to the It's a Material World podcast. I'm Puneeth Upadhyay. I have my co-host David over here, and right now we are surfing through the internet to find graphene-based fun facts, since that is the theme of the episode. So I'm putting all the pressure on David. He is our fun fact guy to give me the strangest fun fact about graphene.
Yes, for the listeners at home, Puneeth did not tell me to have one ready. So luckily, of course, I'm prepared as always. Did you know that there's 3 million graphene layers to make just a 1 millimeter thick graphite crystal?
Wow.
Yeah, pretty
well,
crazy.
How many graphite crystals are there in in a pencil?
Well, it's 1 millimeter thick. I don't know how long is a pencil.
It's 0.7 millimeters thick, I believe. I think you can range with lead graphite.
Oh, interesting. I was totally thinking of like the length direction, not the diameter.
Oh, the
direction.
length. Okay. Yeah.
Oh, so then take the area, do like your circle formula, and then there you go.
Oh my gosh. Okay.
Well, that brings us lovely into our episode for today. So yes, we're going to be talking with a Swedish company called Graphmatech.
Yep.
And they have very interesting technology surrounding how to make graphene more processable. So Puneeth, do you want to walk us through that, and what are some of your favorite parts of the episode?
Yeah, so this one is cool. So we've done a graphene-based episode before. This one's a little different because we focus on like graphene metal composites and graphene polymer composites. So it's the integration of the two for applications. Basically, the way Viktor put it is it kind of keeps a lot of the same processing conditions, but makes things lighter, it makes things electrically conductive. And so it's useful in like energy storage applications or heat exchangers. So that's what I found fascinating. And then this is more just like a personal thing for like MSEs who are navigating their career path. We had a really cool discussion about finding your passion within this space, what to do, what not to do. And there's no failures if you find something that you don't like. It's just something that you kind of cross off the list because this is such a versatile field. So I really enjoyed that conversation. That's something that you should definitely look forward to in this episode. What about you, David?
Yeah, I think that I really like hearing about Graphmatech's approach, especially because graphene is such a touted super material. I feel like it's very hyped up, but it's very apparent that it's a very hard material to apply in like actual real life applications. And so the approach of we're not going to use all graphite, but just get it in somewhere to start like reaping some of the benefits, I think is very important, especially for whenever industry tries to convert from one material to another. Usually it's very incremental, whereas for research, we would want to jump straight to the full graphite to unlock its full potential. So hearing about their process and their philosophy about how to use it is very interesting, and I think can be taken to many other industries that are trying to convert to new materials, but obviously there's lots of hurdles to overcome. So I think that was my favorite part of the episode.
Nice, nice. So yeah, before we get into the episode with Victor, just a reminder, it would really help us out if you leave a rating and review on Spotify and Apple. And we hope you enjoy the rest of the episode.
Hey everyone, we are very excited today to welcome today's guest, Viktor Sanderyd, R&D Manager at Graphmatech. As a material scientist from Uppsala University, Viktor has been putting material insights to use towards novel graphene applications since joining Graphmatech in 2018. He has a strong desire to utilize his abilities within material development to make the world a better place in the long run. Thank you so much for joining us today, Viktor.
Thanks for having me. This is going to be fun.
Yeah, I'm excited for it. And so I know Graphmatech is doing a lot of very interesting things in the material science space. And so we want to dive right into that technology. So obviously the focus is graphene here. So maybe we can just start with the basics. What is graphene? What does the structure look like? And how does that affect its properties?
Graphene is a form of carbon. The element carbon has several different allotropes, meaning different structural forms. I'm sure you're familiar with charcoal, diamond, and graphite, that they all consist entirely of carbon, though their properties are distinctly different. Graphene is yet another structural form of carbon, and it's arguably the most exciting one given its properties. In principle, the graphite that you would find in a pencil tip consists of millions and millions of graphene layers stacked together like pages in a very thick book. If you manage to isolate a single one of those book pages, you have a sheet of graphene, with properties that are far superior to graphite. In fact, these properties are appealing enough for graphene to be awarded a Nobel Prize back in 2010. It was appealing enough for the European Union to launch a €1 billion research initiative in 2013 called the Graphene Flagship to transition graphene into the industry.
So I guess, what are your applications that you focus on at Graphmatech? Because I know there's just a wide variety. I mean, you mentioned the versatility of the space.
While graphene has terrific intrinsic properties, it's also notoriously difficult to reap the benefits of those, since graphene is not a conventional bulk material. In itself, it can't be shaped or formed in any way we want to have it, and it is also immensely difficult to actually isolate these single book pages from the first one. So what Graphmatech is doing is instead that we want to use graphene as an additive to base matrix materials to render composites with improved properties. We essentially want to add chocolate chips to cookie dough to enhance the flavor, the graphene being the chocolate chips. The beauty in this is just a tiny amount of graphene can have profound effects. So this is also a good way, we think, to utilize graphene, since if we do the incorporation of graphene and when we supply raw material that the industry knows how to handle, it will be a raw material for them that they are familiar with, then they can go about forming their parts just as they normally would. But then they would have that chocolate chip ingredient pushing their performances further.
So the one way to add, using your analogy, the chocolate chips to the cookie would be combining graphene with metal to make the composite material. Could you go into this process in more detail and why Graphmatech chose this as the primary way to add graphene into a material system?
We started with metal powder, since actually introducing graphene as an additive is also another one of the things that is easier said than done, since graphene is a really lightweight material. You're not just talking lighter than a feather, you're talking lighter than a hummingbird feather. And you want to combine this with really dense metal particles. I mean, if you would just take those in your hands and try to mix them, they would separate instantaneously because of this massive density differential. What we have done at Graphmatech is that we've developed a method for adhering individual graphene sheets to micron-sized metal particles. We are, in essence, dressing each metal particle in its own little superhero cape of graphene. When these metal powders are then consolidated into an actual part, the graphene will be well dispersed throughout the component. This is the main achievement that we Graphmatech are able to do, that we can add graphene in such a way that it will be evenly dispersed. We're doing this by incorporating the graphene into the metal powder so that they interact with one another in a beneficial way. This incorporation is the core technology, since that allows us to end up with a great dispersion of graphene in the final component. All of the graphene that we're adding will also come to use. This is why we can state that while we're starting from a small amount of graphene, we can produce a large amount of metal graphene powders that will have a major impact on the properties in the end component.
I love the analogies you're using, like the chocolate chips into the cookie dough, or like the superhero capes. I'm just imagining like little metal particle with like a Superman cape. So it's pretty funny. But with all that being said, I wanted to take a step back. So what does this enable? Like, what does the addition of graphene into these metal-based composites allow in terms of like what we could see in applications? Like, what is the versatility there? What is the variety there?
What we want to utilize is the unique properties of graphene, where it is the best electrical conductor ever discovered. It is the best thermal conductor ever discovered. It also has outstanding mechanical performances. So what we're looking to gain from combining this with metal powders is that we want to further boost electrical and thermal conductivity, and we want to tailor mechanical properties. We also want to change properties already on the powder level, where since our powders are used mainly for additive manufacturing, so metal 3D printing, where we have a laser sintering metal powder together. Some metals like copper and silver are highly reflective, meaning that very little of the laser energy is actually absorbed. If you dress metal powders in these superhero capes, or maybe they're villain capes, given that they're black, the reflectivity decreases, so we can utilize more of the energy. We're enhancing both processability, but mainly we're looking for the end property gain, where we're targeting electrical and thermal conductivity, and we're targeting mechanical performance.
And so you did mention that it helps the processability, but also that graphene is a great thermal electrical conductor. So when we think about processing of metal powders, there's a few ways to do it. Does the addition of graphene substantially change the way we process it? And are there any benefits or drawbacks from that?
Apart from what I mentioned about the additive manufacturing of these metal powders, then no, we see the ambition is that the processability for conventional manufacturing, like hot isostatic pressing and conventional pressing and sintering from these metal powders, processing conditions will remain virtually identical. It won't negatively influence the processability. This is also a key aspect of what we're doing, that we need, while we want to boost the end properties, we also have to be cautious so that we're not influencing something in a detrimental manner on the way. Since when we're tuning materials, it's always a complex ecosystem, and we have to be treated very delicately. Because like, you had people bringing rabbits to Australia, and they thought that, yeah, this is going to work out. It did have consequences, and we need to ensure that we don't bring any rabbits to this island.
I guess then, what was your motivation for joining Graphmatech and getting involved in the graphene industry as a whole? Like, what was your background look like?
My background is that I studied material science, I studied chemical engineering within inorganic chemistry at Uppsala University, and I did a master thesis on nanomaterials, since there is something appealing with the word nano, where things you have this realm that you cannot see, where things stop acting the way we anticipate them to be, and you have a universe of its own. And then, since Graphmatech is a startup company spin-off from Uppsala University, it was a smooth transition for me to go into, well, I have this interest in nanotechnology in general, and then you have the coolest material ever discovered. That transition for me was easy to motivate. And of course, what I'm looking to accomplish with nanotechnology in general, and graphene in particular, is that I believe that everyone working at this company, we're here because we want to utilize our abilities for something that is universally good. We know that we're in a state where climate change will is already affecting us in a massive way, and we want to ensure that everyone can have good living standards in the future, while not being at the expense of other organisms or future generations. And we have this effective altruism focus where I want to ensure that using the best of my abilities for something that is, well, actually beneficial for society. And like it is a cliche, but it does help you to go to work even on a rainy Thursday when you really just want to stay in bed. Just having that, just knowing that what I'm doing, it might actually make a difference is a good motivator.
When we talk about different industries and different passions, there's a lot of ways to contribute to your overall goal, which is like the altruism for everyone, creating a better future. And so we're most likely all going to find our different paths. But do you have any advice on how you were able to shape your path to find the thing that you were most passionate about and had the most skill to help move the field?
Whatever you're passionate about, it's always so much easier to motivate yourself to do that. In my case, I would also say that I excluded a lot of things that I realized I don't want to do this and I don't want to do that. And blocking those potential avenues also helped me shape the path I was taking. I also took a couple of gap years and worked in completely different areas before as I started studying at the university, which I also think was beneficial, since I believe that a lot of us, we always have this mentality that the grass is always greener on the other side. But if you've been doing some kind of work, you realize that now I know that I don't want to be doing this. Instead, I would want to pursue with this particular science avenue, and realizing which avenues you don't want to walk down is just as beneficial as realizing which ones that are appealing to you.
Yeah, and I think that's especially important for MSEs because there's so many paths to follow. For me personally, it was like I tried the polymers industry, aviation industry, like medical device project, and found myself most passionate about medical devices. And I remember a term called Ikigai, Ikigai, which is a Japanese concept, which seems applicable here. It's like a combination of what you love, what you're good at, what you can be paid for, and what the world needs. And if you're able to find like that balance between all four, then that's the path you should follow. So it seems to be very similar to what you're talking about, Victor.
Absolutely. I'll sign up for that.
I can only reiterate, I started in one field and then said no way, and then I'm right back in the same field after like 3 years. So it is true, like go check out the grass is greener, and then I found out that it wasn't really that much greener. So I think that's great advice, and something that most people like don't say is that, oh, like it's okay to not like things.
And I mean, also I would argue that of course, realizing that, well, the grass wasn't green here is not in any way a failure. It's just like doing material science in particular. I mean, science is always this iteration where you're taking steps, and then you need to acknowledge that your career is not a 100-meter dash. It doesn't, like, you can come off to what you perceive to be a rough start, but it's still like it's a marathon. You have plenty of time to catch up, and if you didn't take those steps in sideways from the start, well, then you might have ran in the same direction all throughout, and you would always wonder, what if I would have taken those 4 steps in that direction from the start? Where would I then have been? Acknowledging for yourself that our careers are long, and any kind of experience that we gain is always beneficial.
All right. Well, yeah, thanks, Richard, for that great insight. I think that it's really important to hear, especially like Puneet said, there's so many different options. So I think that's great insight. Going back to the core technology of Graphmatech, in addition to metal graphene composites, you also make polymer graphene composites. Could you elaborate on how they are made and the main differences between the polymer graphene and the metal-based composites?
Most of Graphmatech's polymer graphene composites are made through something called melt extrusion. We take solid polymer particles, graphene. These are fed into a heated chamber where you have large metal screws rotating inside to push the material forward. The polymer particles will be very near their melting point, so they are really soft. and the graphene remains solid, basically unaffected by this harsh environment. The high shear forces from the rotating screw will be dispersing the graphene in the polymer melt. These rotating screws are pushing the polymer graphene blend through the extruder, and once it exits at the die, it cools off and renders polymer graphene composites. And again, just as with the metal graphene composites, how the graphene will actually interact with the polymer melt is crucial for the quality output of the composite. The composites that we obtain can then be used as raw materials for conventional plastic part manufacturing, or they can be refined so that you can use them as filaments on your 3D printer at home. In terms of the comparison between the metal and polymer graphene manufacturing, one of the main differences is with polymers is that the properties that we're trying to enhance when we talk about electrical and thermal conductivity, they are really, really poor from the start in polymers. So we have lots and lots of room for improvement, but we also won't get any assistance at all from the base material. Whereas in the metal side, we start from a good level and we're trying to push this a bit further. So the degree of improvement for instance, electrical conductivity is orders of magnitude. So we can actually render polymers electrically conductive, but they will still not be near that of really high conductive metals. Pushing them a long way, but we're not pushing them all the way to materials like copper or aluminum.
So then what can polymer graphene composites be used for? And how much of a difference is that between metal graphene composites?
Polymer graphene composites can be used for partially we have the electrical conductivity, and we're also influencing mechanical and thermal. So we're talking about multifunctional additives, graphene being a multifunctional additive, where we're actually we're tuning not one single property, but we're tuning a broad aspect of properties. These are used, you might ask, why would you want to have electrical conductivity in a plastic? Well, you have all kinds of gaskets and liners that needs to be electrostatically dissipating, since you need to be able to discharge static electricity. And nowadays, this is done by an additive called carbon black, which is essentially a residue from fossil industry. And what you can do with carbon, like graphene can do anything that carbon black can do in a heartbeat. And it can also go beyond just electrostatic dissipation. We want to be able to manufacture sensors and things that are actually using electrical conductivity to a much larger degree than what is currently possible in a polymeric material. We're also looking at gas barrier properties, since we have hydrogen industry in transitioning from fossil fuels to hydrogen. That's all good and well. It's one major building block in that challenge. So we're storing hydrogen in highly pressurized vessels, and nothing is penetrable for hydrogen gas. It will diffuse out from there. So if we can prolong the time it takes for hydrogen gas to diffuse out, then we're doing something good, since hydrogen gas in itself would otherwise, if it's in the wrong position, it will have a negative influence on the climate. We want it to be inside these pressurized vessels. If it's leaking out, well, it's not doing much use. But sorry, I was drifting away from you. Your actual question was the differences between what the polymer graphene composites can be used for and the metal graphene composites can be used for. Then what we want to do with the polymer graphene composites right now is we're using this as master batches. Essentially, you have a concentrated chunk with as much graphene as possible that a polymer compounder can use to dilute their specific polymer grade, and then they will reap the benefits from the graphene that we added here. So you can get a decent degree of electrical conductivity. So you can go beyond electrostatic dissipation, and you can also, while also improving mechanical properties, improving thermal properties, and changing the gas barrier properties. And whereas from the metal side, the same words keep reappearing, the electrical and thermal conductivity and mechanical properties, though the applications look a bit different, because when we're talking thermal for metals, you're talking heat exchangers, and you have heat exchangers in everywhere. I mean, your computer at home, you have heat exchangers in nuclear power plants, in like anywhere that you have a machine operating, you will have heat exchangers. Some of these are in really harsh conditions, like they might be operating by the sea in salt water, where not many metals can actually function. I mean, we have great thermal conductors. Copper is a terrific thermal conductor. Aluminum also very, very good. If you try to put those in salt water, they will not operate very long. Instead, you have to use specialized steels, typically high in nickel content. And these are great because they survive in these harsh environments, but they're actually really poor in thermal conductivity. So you had to compromise with the main property that you wanted to have just to get something that could survive in those environments. Such a material is appealing for us to work with because the graphene is going to survive in the environment, no issues. And then if you can take something that is decent, then we could probably push this quite a bit. So those kind of heat exchangers would be appealing for metal graphene composites.
Yeah, very interesting. But you mentioned energy storage vessels, which I want to go back to and dive into a little bit. So you said graphene is impenetrable to hydrogen, which makes it great in these applications. Can you compare that to like the current traditional materials used in these energy storage vessel applications right now? Is there any like quantifiable improvement that you know of or qualifiable at this stage that you would be willing to talk through?
I mean, we can say that we use in high density polyethylene, which is one of the materials commonly used for liners in pressure vessels. We see 40% improvement when we add graphene into this. And of course, that's quite a significant number. When we're talking about what this gas barrier property for that actually means, and we can imagine that hydrogen molecules, which are, I mean, the lightest element that we have, is the smallest atom that we have. And it comes in as hydrogen gas, H2. And you mentioned graphene is virtually impenetrable for graphene. Hydrogen will make its way through anything apart from graphene under certain conditions. Normally, a polymeric liner in a pressure vessel, it consists of polymer chains. You can think of this as a block of spaghetti, each spaghetti strain being one polymer chain. And the hydrogen molecule will need to find its way through this nest of spaghetti strings. Unfortunately, the hydrogen gas doesn't, most of the time, it can actually go straight through the spaghetti strains. It's not even an obstacle for them. So what you want to do when you're constructing gas barrier liner, you want to add more obstacles so that the hydrogen needs to go around it, or at least take longer to pass through it. And this is the conventional way as well. We're not changing, we're not doing something revolutionary in the approach. We're adding graphene as obstacle for hydrogen diffusion. The difference is that this is a very long and a very, very difficult obstacle for hydrogen to navigate through. So it has to go around it. And the longer the path for the hydrogen to diffuse, the longer time it will take, and the longer we will have the hydrogen gas inside the pressurized vessel where it belongs. And we see that graphene is a very suitable additive for this cause.
And so would your graphene be implemented in a polymeric solution where it would replace that liner, or could you remove the lining entirely and just make a metal composite that now has the graphene on the surface layer?
There will still be a need for the polymeric liner. And then what we're working on is to, rather than using the conventional polymeric material for such a liner, we would want to use graphene-boosted polymeric liner. It's because a pressurized vessel still has this outer shelling in metal, then it has the inner liner in polymers, which is like every material design. It's a trade-off because it needs to accomplish many different things. And the polymeric liner will still be there, but we want to add some chocolate chip flavor to it.
Cool. So do we want to talk about, I guess, electric vehicles? I think that's like the next step. You mentioned energy storage vessels. So how could that potentially lead to, or I guess like you need a lot of pure metals like copper and aluminum to put an entire fleet of EVs onto the road. So how can your technology be used to solve the problem of meeting that demand for this like supply, to meet that kind of relationship there?
The materials, as we touched upon earlier, was like they will be a vital part in mitigating the consequences for the ongoing climate change. And one of these challenges that we encounter is the way what you're describing, that, well, electric vehicles are great, but now we have a demand for more materials than we might actually be able to supply. And this puts pressure on improving materials. And what we want to accomplish with metal graphene composites is to be able to use less material and obtain the same properties. So if we can reduce the amount of copper and aluminum that each electric vehicle would need by a certain percentage, then this will of course help in that less of the base metal is needed in the first place, but it will also help in, well, we're reducing the weight of the vehicle as well. So we'll consume less energy while this is driving around. The main purpose for metal graphene composites is to be able to use less material and maintain the same properties. And we need to do, in order to do this, we need to be better than what's currently out there.
How much less of the base metal would, like, I guess that's very dependent on the application, but generally how much less?
It's that is actually is a question that I can't answer with a straight face, since it's so many variables. But of course we and it's also something that if we would have been at a level where we could take an electric vehicle and show the graphene enhanced electric vehicle right next to it, and that being 50 kilograms lighter, then Graphmatech wouldn't just be a startup. Then Graphmatech would be the size of a large electric vehicle manufacturing company.
Yeah, I think one thing that I personally know is that there is a lot of like metal in a battery that you wouldn't think of. So like in a sizable battery of your car, it's like 3 meters long, like a couple meters long of material for your cathode and your anode. So we're talking about like upwards of 5 meters of this metal sheet and a thing that you can hold in your palm, which is an insane amount of metal. And then on top of that, it's like 10 microns to 20 microns thick. And so you have this insanely thin and long sheet of metal that goes into each battery. And so I think that as someone with experience, like if we could reduce that even more, like that's insane. And so now with graphene, you can create a more ductile metal where aluminum and copper at such like thin amounts become very brittle and can break easily. And so there's a lot of benefits I think that can also be understated here, because it's hard to imagine so much metal going into such a little container.
Absolutely. But I mean, if you're curious, you can always crack open a battery at home. Be careful, but
yeah, I think we need
actually, there are people on YouTube already doing this, but you can watch one of those videos. They're quite educational to get an understanding for which amount of material design that is going into this, which amount of metals that any battery actually contains. And yeah, I mean, there's hundreds of kilograms of pure metal in an electric vehicle.
Wow, yeah, I just love touching on that. But I think that we just touched on 2 applications, but this is just scratching the surface of what the full potential of graphene can be. For example, pristine graphene properties are far superior than the properties of the graphene that Graphmatech uses right now. How far off do you think we are from unlocking the full potential of graphene, and what steps is Graphmatech taking to achieve these goals?
This is, of course, also it's difficult to answer when we reach the rainbow, but any progress in materials technology is this result of these iterations. We are taking steps all the time. The challenge is realizing if are we running in the right direction? Are we running 100-meter dash or we're running a full marathon, and then to prepare ourselves accordingly to set the expectations. The beauty with graphene is that, as you mentioned, like we are really just touching the surface. We don't understand the fundamentals of why we have these outstanding properties even. And there will be so much exciting work in the coming decades where graphene is transitioning itself to the industry and making its mark in everything from consumer electronics to bulk materials. And the steps that we have, the closest steps that we have is that, I mean, we are progressing in manufacturing graphene from the first place. We are progressing in how we can incorporate this into other materials, and we are progressing in getting this to be industrially adopted. I mean, Graphmatech, we're trying to act like we're acting as sort of an industry enabler, because graphene itself is difficult to handle. It's difficult to use. It doesn't behave like anything you're used to. It's a super light, fluffy black powder. This is difficult to use. Most industries take one look at that and go, no, can't really incorporate this. What Graphmatech is doing is that we are taking the difficult part of this unconventional material and we're dishing it out to be something that the larger industries will understand. This is a conventional raw material for them now. When we take metal graphene composites, when we take polymer graphene composites, this other industries know how to handle. So then they will go on and make components from this. And in the more components that are being made, the more end properties we see where graphene has these desired effects, the more the demand is going to come upwards in the supply chain. And the more, the faster these iterations will be made. So, and the faster the wheels are turning, the better the graphene is going to be. If we're considering that mankind has known about steel for thousands of years, we made carbon steels thousands of years ago, and we're still developing new steel grades, and there's still so many things that we are discovering about steel. Graphene is literally a teenager since it was discovered. So that I'm saying that to put it in context, that it's we will not unveil the full potential of graphene in the coming few years, but we are taking large strides and we will continue taking these steps. But as a researcher, I also find it motivating that to know that it's not going to end. We're not going to hit this wall where we stop discovering new things. There will be many discoveries to be made for graphene during our lifetime and for coming generations, for sure.
Yeah, I mean, I like the perspective you put on it compared to steel and the decades of just like manufacturing, refinement, and improvements to that process. Like graphene is very much in its early stages, so there's a lot of potential. So with all that being said, maybe to wrap up the episode, what advice would you give the next generation of MSE students who are interested in graphene, such that they can kind of take those steps and get involved in the industry and make significant strides?
Yes. Well, I mean, since one of the benefits with graphene is that it's going to influence so many sectors, and many of which we have yet to discover. There is a plethora of scientific articles out there now exploring graphene, both from a fundamental level, but also in order to understand how these ordinary carbon atoms can yield such astonishing properties, but also for all kinds of applications. You have from antibacterial effects on implants or medical devices in the human body to quantum computing and everything in between. And we're still just scratching the surface. Really, regardless if you're interested in physics, chemistry, biology, electronics, any other science or engineering field, there is a great likelihood that you can encounter graphene if you pursue studies in either subject, since there will be graphene-related discoveries out there for you to make.
Thank you so much, Viktor, for joining us today. This was a really interesting episode. I like the comparison between the polymer graphene composites and the metal-based composites, and we just really appreciate you joining us today.
Thanks a lot. It's been a pleasure. And all the best in the future.
Thank you. As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.